Hi. So today um I want to talk about two problems I've actually thought about for quite some time. So one of them is an old problem I didn't solve here, but I which was like about 1.5 months ago, and another is a more relatively new problem. So since I've already thought about them, I'll explain the questions and explain the thinking, I guess. And I've already seen the solutions. Um, so let me share. Okay. So the first problem is called um one sec. So the first problem is Codeforces around 866 div 2, problem D, and it's called the butcher. The problem is as follows. You're given a bunch of rectangles, right? And that is basically you're given 2 into 10 to the 5 rectangles. So for instance, you could have been given these rectangles. 1, 3, and so on. So for instance, you could have been given these 3 rectangles. The claim is that they come from a big rectangle. All of you've been given pieces that come from a big rectangle. Following the following the below process. Following the below process. So somebody has taken a big rectangle, right? And picked either a horizontal direction or a vertical direction and made a cut. So they either cut vertically or horizontally and at some integral point, right? So suppose this is 0, 1, 2, 3, 4, 5, right? They say cut it here. They threw away one of the pieces, let's say this, and then repeated the process here. Picked either a horizontal or vertical direction and made a cut, right? Threw away this piece, again, picked horizontal or vertical and made a cut, and so on. Now, this is the process, and given these small rectangles, you have to give as output possible big rectangles it could have come from. Okay, right. So yeah, I actually wasn't able to solve this. But these are the these are the ideas that get thrown around when you see something like this. The first idea is, okay, when this person who took this big rectangle that you don't know what its height and width is, they have two choices. Like their first cut, they have two choices, right? You can either pick horizontal and vertical. If they do pick the horizontal direction, right, then there must exist a piece with, okay, let's say H prime and W prime must exist a piece with W prime. If they pick the vertical direction, then so if they picked horizontal direction, if they picked vertical direction, there must exist a piece with H equals H prime, right? So that's the first idea. The second idea, I guess, is, okay, no, let's continue on this first idea. So what this tells us is if you see if they had cut horizontally, then the largest width you see is the width, right? The reason being, that's the guy that was never cut vertically, so it must have been that must be the width, yeah. And same here in this case, the largest height you see is the height. Okay. And another thing we realize is that like you've been given all the pieces, and the area of the cut rectangle is the same as the area of the original. So the area is fixed. So in case one, assuming there was a horizontal cut, you know the width and you know the area. So then that automatically gives you what the height is. Same way, in this same thing. In this case, you know the area and this automatically gives you the width. So really there are only two potential rectangles, right? Because there's only one, in one case, height is fixed, and in the second case, width is fixed, but the other element also gets fixed. So there's only two possible rectangles. So you have H1W1 and H2W2 as potential rectangles. Now, all you need to do is check whether these could have been possible. There was some cutting that could have taken this H1W1 to the pieces they give you, and some cutting that could possibly take this H2W2 to the pieces they give you. Okay. So how do we do that? The idea is as follows. You take your original rectangle. So we're checking case one, right? So this is the horizontal case and this is the vertical case. So you take your original rectangle, right? And this is the case where the width was fixed. So you just pick the guy with the largest width and take them off. Okay. So now you have some H prime and W prime left. Now, so this is amongst the others, you find a guy that either has the same height or the same width. Now, if there is a guy with same both, the algorithm has to stop, right? Because there's a piece with both of these, that means like this was the next cut. So assuming you'll find some guy with any one, you might find you can't find one guy with, okay, so okay, maybe let me write this. Only H prime, only W prime prime, one rectangle with H prime prime, W prime prime, two rectangles, one with H prime prime and one with W. Okay. So if you find some guy with only H prime prime, okay, what I'm doing is I'm describing a greedy algorithm and then we'll prove why it works. But first I'll describe it. If you find some guy with only H prime prime, then take that as the next rectangle, cut it off. You'll get H triple prime, continue the algorithm. And and the last guy has to equal H and W, and that's when you stop. So if you see only H prime prime, continue the algorithm. If you see W prime prime, continue the algorithm. You see one rectangle with H prime prime and W prime prime, stop. This has to be the last one. If not, it's not possible. If this is the last one, It's possible, else not. This particular H prime and W prime are not possible. If you see two rectangles, one with H prime prime and W prime, note that this couldn't have been possible because if you have a rectangle with H prime prime, that means a cut was made, a vertical cut was made, right? That means that the next rectangle definitely cannot have W. And similarly for W, if you see a rectangle with W prime prime, definitely a horizontal cut was made. So therefore, you can't see something with H prime prime. So this case is not possible. So this is a greedy algorithm. Now, obviously, if this algorithm works, I mean, if you go to the end and you do see that everything fits, then the big rectangle was a valid possibility. I don't think there's, because I just showed one way to go from the big rectangle to the small ones. But I just picked the greedy algorithm, right? So what if it didn't, if it doesn't work, why does it mean that this big rectangle, the small rectangles couldn't have come from the big rectangles? Let's see. So if you get a yes, clearly it is get a no. I guess we show that any cut is equivalent to the greedy cut. Right? And the way we show that is, so like assume that they were making whatever cut they want, right? Like assume someone with this big rectangle. Okay, maybe I'll write this below. Maybe, yeah. Claim is that the greedy cut is the only possible cut. Why? So someone has a big rectangle, let's say, and they decide to cut somewhere. Then there will be a piece that where it equals its width and or equals its height, right? And so if they cut horizontally, there's a piece that equals the width. And if they cut vertically, there's a piece that equals the height. So, and this is true as you continue as well. So the next cut they make, either the piece will equal this height or this width, right? And we showed why if they make a cut, there cannot be pieces equaling both. And we showed that if there is one piece that has the same height and width, that's when the algorithm ends. Yeah, that's not like formal or anything, but that seems fair. Yeah, should be only one. If there are if you see two possibilities, it means that you could not have obtained it from them. Okay, so I guess that's not as much of a proof as I would like, but if the person did cut it, and when they cut it, they obtain a piece where the height is equal or the width is equal, and all we're doing is checking that piece and determining what cut they made. And because there could only be one such piece, because if you cut via height, the width is, I mean, if you cut horizontally, the height is changed, and if you cut vertically, the width is changed. So I think that's fair. So I wanted to look at, so one thing I'm a bit iffy about is how this was implemented, right? Because now what you need to do at every step is you need to, amongst all your points, check whether there exists a point that has a given height. There's no point sorting by heights or width. One idea, the two ideas I had to implement this is, one is just make a vector of 10 to the 6, right? And one for heights and one for widths. And at the right element, store all the guys with the correct height. And just go check whether someone exists there. And same for width. And when you delete someone in the height, you need to go over the list of widths and delete someone. But that is not nice. Yeah. The other thing, I guess, is have a set with both height and width so that you can find guys with a given height, delete them, then find guys with a given width, delete them. So it should be fine. Yeah, I think I can use a set, but if there are repeats, yeah, I guess a multi-set or something. And when I find elements, I think I just need to check if the second element is equal. So yeah, those are the ideas for implementing. I just wanted to look at an actual both the editorial and the code. There's some contest going on. It usually takes a lot of time when there's contests. Oi. Oof. That is bad timing. Yeah, I can't lose this either. Lose this as well. Okay, so I will implement that when, I'll look at that editorial when I'm able to. I guess the other thing I've been thinking about for a bit, which I did not, like, I actually tried to solve this 2 months ago, but it's confused. And I think there's a trick which I didn't think about, and this is finding number of subsequents that equal a given XOR in OFN time. So let me state the problem. Let me new share my. Okay, so I'll try to implement the previous problem when I'm able to see the editorials and stuff. Right now I'm just trying to explain this other problem. So this is Codeforces round 841 div 2 problem C even subarrays. So the problem is, you're given an integer array. Find the number of subarrays whose XOR has an even number of divisors. So the first thing is it's the numbers who have even number of divisors. So if you take the number 12, for example, 1 into 12, 2 into 6, 3 into 4, right? It has 6 divisors. If you take the number 16, 1 into 16, 2 into 8, 4 into 4, has 5 divisors. So what happens is all squares end up having odd number of divisors and non-squares end up having even number of divisors. So literally you just need to find number of subarrays whose XOR is not a square. Okay. And the constraints, so you're given an array, the constraints are as follows. Yeah, so you're given the length can be n, where n less than equal to 2 into 10 to the 5. Each element ai is also less than 2 into is less than equal to n, right? Those are the constraints. So you need to be able to find, basically you need to be able to find number of subarrays that don't XOR, number of subarrays that XOR to a non-square. So what you can do is, I guess, the largest, okay, so suppose you have a is less than equal to n, right? Then the number of bits that this guy uses is log n floor, right? Because say n is 16, I think log n plus 1. Sorry, what am I saying? Okay, what I'm trying to say is, what is the biggest XOR value I need to worry about? I guess that's what I'm saying. I think it's 2n, but I want to say that rigorously. Okay, so if I know a is less than equal to n, what are the maximum bits that a can take of bits? So in like, I guess the worst case number of bits happens when n is a power of 2, and in that case you end up taking log n plus 1 bits. 1 bits, right? Because example 16 is 1 0 0 0 0. Yeah. 4 0, yeah. Log n plus 1 bits. And the worst XOR would be when all of this is 1, right? So that's just log n plus 1 ones, which you can imagine is just 1 less than 2 in the log n plus 2 position. So that would be 2. So if you have, okay, so 0 indexing in the log n plus 1 position. So it would just be less than 2 to the log n plus 1, right? Which is equal to 2n. So that seems fair. How many bits am I using for this? Or did I make a mistake? This XOR is definitely less than 2 to the 5. Yeah, okay, seems fair. So 2n. So I just need to worry about the number of squares less than equal to 2n, right? So how many squares do we have less than equal to 2n? I should hope not too many. But yeah. How do I count that? Yeah, I just find the nearest square to 2n. So yeah, the number of squares less than n should be square root n, guys, right? There should be, yeah. But is that too much? I feel like the square root of 2n squares, and I want to do a times n operation because and n is something like 10 to the 5. Should be okay. It feels like it's hitting the limit. But okay, there's these many squares. So all I need to find is for each square, the subarrays that number of subarrays that XOR to the square, right? So finding number of subarrays that XOR to a given n can be done in O(n) time as follows. The idea is if you have, say you're at this point and you find that the XOR of the subarray is P. And you're wondering how many you want to count the number of subarrays that XOR to n. Then if you find a subarray that XORs to P XOR n, then you know this guy XORs to n, right? So the point is when you reach from the beginning to some point, if you have a subarray XORing to P, from the beginning to here, then you just need to count the number of guys before it that XOR to P XOR n. Okay. So the way you can do this is, and since we know that the maximum XOR is 2n, so we can just keep an array of size 2n. And here we can keep a count of how many guys we had XORing to the index, right? So 1, 2, and so on, and how many guys we had XORing to this given number. But here's the thing, if you if you try to fill up this array first, find the number of guys XORing to every element, you can't neatly like go over each P and find the number of guys before P who XORed to a given number which we want. So the idea is not to fill up this number of XORs. Okay, this is a crappy explanation, I'm very aware. But okay, let's try to improve it. Okay. So say Ci contains number of subarrays starting at 0 that whose XOR is I. Okay, for your original array. Of A. Okay, this is A. And what we are trying to do is count total subarrays that XOR to n. And you might think, let's fill up the XOR count array and then use it. But that doesn't work, right? That doesn't work. I mean, that's not clean. Maybe there is a way to make that work. But because our algorithm is good, when you reach a position n, figure out all the guys. I mean, when you reach a position P, figure out all the guys and say its XOR is, you reach a position and its XOR is P, figure out all the guys less than P whose XOR was P XOR n. So this at your Ci array at the P XOR n position should contain only guys less than here whose XOR was P XOR n and not the guys like the arrays extending to here, right? So therefore you need to keep filling this as you're doing this. And I guess that is the key to the subarray count. I think you can do it even if you like do the whole thing, but I don't know. I feel like there's some double counting and it's a bit more complicated. But if you do it as you're filling, then you can just count for every XOR value you get, the number of guys before that who were of the form T XOR N, so that. And what does the edge case look like? I guess you always want to have one guy, just put one guy in 0 to begin with, so that when you reach here, you, if this was N, you go counting, you go looking for the number of guys with XOR 0, and you count this as well. Yeah. Or you don't need to do this. You can just, yeah, count this. Yeah, I think that works. Let's see what is the status with this Codeforces business. Yeah, it says it's some browser being checked. I feel like this I've seen the code, so I can start coding this up. Yeah. I shouldn't have lost the question. Maybe I remember it. So we first want a function that tells you, oh, it's not int actually. Number of subarrays could be a lot. That tells you a um and in X, the number of it returns number, this thing returns number of subarrays of A dot sort to N. Yeah. So here what we do is first I have a vector int. Oh, let's not use N because the number of like something will be N. So now we need the cumulative sum array. Sorry, the number of XORs of a given value. Should be int XORs, and how many guys do we want here? N minus 1 should be actually fine. We're on the cusp, but that's okay. And I want to have XORs of 0 as 1. Okay. Then if I equals 0, I less than a n, yeah, plus cursor equals 0, right? So cursor equals cursor. This is how you XOR, right? Binary. I think so, yeah. A of I count plus equals source of cursor XOR X. And then updating the cumulative array XORs of cursor plus. Return count. Okay, that looks good to me. And C in N in A N in I yeah. Is zero considered to have order even the dimension? Okay, I can at least see. Oh, this is only for. Okay, let's just guess. Is zero uh zero has no divisors? I don't think it counts. Is one. Or zero has all divisors. Yes, it's confusing. I into I less than q and I equal. And I into I. So what is the total number of subarrays? I think it's n into n plus 1 by 2, right? Including the out is equal to n. Oh, n is in integer. That's annoying. So let's go to Yeah, that actually seems fair. I think this is okay. Yep, I guess I will try the other one when Codeforces is up again. Thank you for watching. Bye.